So today we're going to talk about predicting products for single replacement reactions and double replacement reactions. Before you watch this video, make sure you watch the video on solubility rules and activity series. You need to know that because our single replacement reactions use the activity series and our double replacement reactions use solubility rules. So today for single replacement reactions, we're only going to look at the 3A and 3D. Again, these are in your reference packet for you. There are two other ones, 3B and 3C, and we'll talk about those in class, not right now. So basically, what we need to do is we need to follow the generic formula of A plus BC yields AC plus B. Now we can do that a few different ways, and the first one is our metal-metal replacement. So in our metal-metal replacement, one of our elements is a metal, the one that's by itself, and then we have a compound. What we're trying to do is we're trying to see if the metal that's just the element can switch places with the metal in the compound. This is only going to happen if the metal that is in elemental form, if it is more reactive than the metal in the compound. And for that, we need our activity series. So our activity series is in our reference packet, and what we want to do is we want to look up zinc and copper. So I look up zinc and I look up copper, and zinc is higher on the activity series, telling us that zinc is more reactive. Since it is more reactive, the two are going to switch places. If zinc was less reactive, we would have no reaction. But in this case, we do have a reaction. So I'm taking zinc, and that's going to pair up with nitrate, and then I have copper that has been kicked out. Now you guys know that whenever we form a compound, we have to form a neutral compound. So zinc has a +2 charge, nitrate has a -1 charge, so this compound is going to become zinc nitrate with a 2 subscript. Then you know that we need to have a balanced reaction, and everything here is balanced. Our second type of single replacement reaction that we're going to talk about today is our halide-halide replacement. The way you know that you're doing a halide-halide replacement is because the element that by itself is a halogen. If you have a halogen that is by itself, then it's going to try to switch places with the halogen in the compound instead of the metal. And you do the same thing here. We go to our activity series, see if the halogen that's by itself is more reactive than the halogen in the compound. Here, chlorine is above bromine, so these two will switch places. So we're going to have lithium chloride plus bromine. Now again, we need to create a balanced reaction. So I'm going to I have 2 chlorine, so I need to put a 2 coefficient out here. And I'm going to need a 2 coefficient out here because I have 2 lithiums and 2 bromines on my product side. So that's single replacement. Next we're going to talk about double replacement. And here we need to look at our solubility rules. Basically what we're doing here is we're going to be switching our 2 cations, forming neutral compounds, and then seeing if products will come about. So what we want to do first, we're going to switch our sodium and lead. So if we switch it, lead is going to pair up with sulfate, and then sodium is going to pair up with nitrate. We need to make neutral compounds. Pb here has a +2 charge. If we look at our previous compound, sulfate has a -2 charge, so we only need 1 of each. And then sodium has a +1 charge, nitrate has a -1 charge, so we're good there as well. Now we want to balance out our reaction. If I have 2 sodiums on my reactant side, I need 2 on my product side. That makes me have 2 nitrates, and I have 2 nitrates on my reactant side. I have 1 sulfate, 1 lead, and 1 lead. So we figured out our products, but now I need to figure out if this reaction really occurred. So what we're going to do is we're going to use our solubility rules and see if PbSO4 is going to be a solid or aqueous. And then we're going to check sodium nitrate and see if it's solid or aqueous. In order for this reaction to actually occur, one of the products must be a solid. If both of them are aqueous, we write no reaction. Alright, so I told you guys that I like to look up the anion. So I'm going to find sulfate on my solubility chart. And it says, on the soluble side, all sulfates except calcium, strontium, barium, mercury, lead, 2, and silver. Well, in this case, I do have lead too. So that's going to make this one solid, because it's one of the exceptions on my aqueous side. Then I look up nitrate. Nitrate is my other anion, and it says all nitrates, acetates, ammonium, and group 1 salts are soluble, so this one is going to be aqueous. Since one of my products is a solid, it did occur. The next type of double replacement reaction is an acid-base neutralization. So acid-base neutralization has an acid and a base, and it forms salt and water. You figure out something that is an acid because it starts with hydrogen, and you know something's a base because it has a hydroxide ion. So what it's going to do is it's going to form a salt and a water. So basically the metal and the anion that's paired up in your acid, those two are going to come together, and the rest is going to be water. So I have calcium and phosphate. Now we need to crisscross our charges in order to create a neutral compound. All right, so calcium has a +2 charge, phosphate has a -3 charge, so we're going to end up with Ca3PO4 plus water. Now what we're going to do is balance out our reaction. So hydrogens, I would do last since there's hydrogens in multiple places. I would look at phosphate next. So I have 1 phosphate on my reactant side and 2 on my product side. So in order to balance that out, I'm going to need a 2 coefficient out in front. Now my calciums, there's 1 on my reactant side and there's 3 on my product side. So I'm going to have to put a 3 in front of my calcium. Now I have my H's. Let's do those next. So I have 6 hydrogens from H3PO4, and I have another 6 hydrogens from CaOH. So that's a total of 12 hydrogens. So I'm going to need a 6 in front of my water. Then I want to add up all the oxygens that are not involved in the phosphate. So I have 6 for my water, and that's it on this side. And I have 6 for my calcium hydroxide, so we are good.